I now have the pleasure of introducing Marcos Mariño from the University of Geneva, who will be giving a mini course on resurgence and quantum topology.
What is the pointer? Okay.
In the meantime, you can pass with this.
Okay.
And you can take off the mask.
So where do I? How do I advance here? Okay. Very good. Okay, thank you very much for the invitation to give these lectures. It's a really great honor to be here. So I'm going to give a mini course on resurgence and quantum topology. Probably not many of you are familiar with the subjects. So I'm going to, the course will be essentially have two parts. The first part will be an introduction, a kind of short introduction to the general theory of resurgence, and then I will apply this theory to a very interesting problem appearing in quantum topology. More precisely, a problem appearing in the theory of quantum knot invariants. So the slides, the PDF files of my slides can be found in my web page. So this is the direction of my web page, and you can also find there a written up version of the talk. So in this way, you don't have to write anything, because I even wrote the notes for you in my web page, so you will be able to find it there. Okay. Okay, so let me start with an introduction. So what is this about? Well, the starting point of my discussion will be perturbation theory. And if you have taken courses on physics and mathematics, you know that perturbation theory in a small parameter is one of the few universal analytical tools that we have to solve complicated problems. When you don't have an exact solution in physics or mathematics, very often you have to use perturbation theory. And one example that you probably have already studied when you were taking courses in undergraduate quantum mechanics, and it's probably one of the simplest examples that you can find of perturbation theory, is the Quartic oscillator in quantum mechanics. So in quantum mechanics, you typically face your first solvable model, which is the harmonic oscillator. So the harmonic oscillator, I don't have a pointer here, but it's coming. So the harmonic oscillator is corresponds to a Hamiltonian, which is pi squared over 2 plus x squared over 2. And this is one of the first examples in quantum mechanics. Okay. So. Oh, okay. Very good. Okay. Oops. Okay, so the harmonic oscillator is just the first two terms in this Hamiltonian, and this is an exact model, but of course in quantum mechanics, we don't have the luxury of having exactly solvable models in all situations. So very typically you can have a Hamiltonian in which you add a harmonic term, gx to the fourth, so you can think about g as a small perturbation. So if the value of g is small, you can think about what is the spectrum of this Hamiltonian. So you know how to solve the spectrum of this Hamiltonian when g is equal to 0, and you want to solve at least approximately the spectrum of this Hamiltonian when g is different from 0. And I have to say that already in the first paper on quantum mechanics by Heisenberg addressed this problem, not for a quartic perturbation, but for a cubic perturbation, and he developed already the basis of perturbation theory in quantum mechanics. So what you can do, and this is something that we teach our students to do, is to calculate the energy levels of this Hamiltonian as a power series in G, okay? So in my convention, when h bar is equal to 1, the ground state energy of this system is going to be 1/2, which is the value that you would obtain when G is equal to 0, and then you would find a formal power series in G with higher and higher powers of G that you can compute more or less systematically, and this is one of the things that you are taught when you study quantum mechanics. Okay? And this is in the power of perturbation theory. You don't have an analytic solution for this problem, but you can at least construct a formal power series solution for the ground state energy and also for the excited state energies. Okay? Now, what probably they didn't tell you in your course on quantum mechanics is that this is a little bit of a cheat, because these power series are actually not really well defined. So when you actually compute a lot of coefficients of this power series, you realize that the coefficients of this power series actually grow factorially. Okay? So a formal power series in which the coefficients grow factorially has 0 radius of convergence, and this means that this formal power series doesn't really define a function. So in principle, you don't have an object which is mathematically well defined, and you don't really know what to do, okay? So this is what they don't tell you, and of course, it turns out that with a little bit of work, you can actually make sense of these things, but one clear message is that making sense of these things is not a trivial, thing, because if you don't have a series with a finite radius of convergence, you have to work a little bit more to know what to do, okay? So more precisely, you have to admit that if you have a series whose coefficients grow factorially, you don't have functions, and then you have to do something about it. And it turns out that this situation is not special, but rather generic. Most of perturbative series that you compute in quantum theory are actually of this type. The coefficients grow factorially, and then you don't have really well-defined functions. Now, as I said, you know, we don't teach these things for fun, because you can actually make sense of these things, but to do that, you have to work on it, and physicists and mathematicians have developed many tricks to make sense of this divergent series. And probably the most compelling and encompassing theory to do this is what is called the theory of resurgence. The theory of resurgence was developed by many people, mostly in the 1970s and 1980s, as a general framework to address this problem. And let me also remind you that most of the calculations that you do, for example, in quantum field theory to try to match the results of experiments done at CERN, so a few kilometers from here, are also based on perturbation series. So if you want to really understand what are the predictions of physics in real life, you have to have some idea of how to make sense of these divergent series, okay? So the theory of resurgence has a very abstract mathematical aspect, which was developed mainly by the French mathematician Jean Écalle. And Jean Écalle constructed his theory in the late 70s, early 80s by synthesizing many developments that were mainly due to many physicists. So there were many people who worked actually on the structure of perturbative series in quantum mechanics and quantum field theory. Let me mention some people like Carl Bender and T.T. Wu, who were the first people to actually notice that this type of perturbative series, like the one I showed you for the quartic oscillators, were actually factorially divergent. Then André Boros did very important mathematical work which led to this theory of resurgence. And then in quantum field theory, there were very important contributions by Giorgio Parisi and Jean Saint-Justin. So the theory of resurgence builds on this work, if you want, this heuristic work, mathematicians and physicists, in order to extract a general theory of perturbative divergent series and how to make sense of them. Now, in the last years, this theory, which is, as you can see, this theory addresses many basic problems, so it's quite established in a sense. But in recent years, we have seen many new applications of this theory to realms that were essentially not considered at the very beginning, and in particular, there have been many interesting connections with a very different realm in mathematics, which is geometry and topology. You could think that this theory of resurgence would be more related to functional analysis, and it is, but in recent years, it has been noticed that there are many connections to geometry and topology, and in particular to quantum topology, to invariants defined by quantum theories and quantum field theories. Now, in these lectures, as I said, I will present first some general ideas of the theory of resurgence, and then I will apply them to problems arising in the study of knot invariants. And I want to mention that this combination of the theory of resurgence with knot theory was actually pioneered by my friend and collaborator Stavros Garoufalidis. And I will actually focus in the second part of my talk on a perturbative series that appears when you consider the Jones polynomial. So the Jones polynomial is a famous invariant of knots, which was introduced by Vaughan Jones in 1985. So this is Vaughan. And I have to say that these lectures should have been given by Vaughan. This was the original intention. But unfortunately, as many of you know, Vaughan passed away a few months ago. And I would like to dedicate these lectures to the memory of Vaughan Jones, who was a very inspiring figure for many of us. And I have to say that the first time I met Vaughan was actually in the Jones Research Symposium in Lisbon many years ago, when I was giving a talk also on knot invariants. And he was extremely receptive and extremely supportive. And it's very moving for me to be able to give these lectures here in another Jones Research Symposium to the memory of Vaughan Jones. Okay, so let's start. So let's start with some kind of formal definitions. So in these talks, I will always denote formal power series by Greek letters, so phi of z. Z here is a parameter, so it could be a coupling constant in quantum mechanics, a coupling constant in quantum field theory, it could be a parameter in a differential equation. And so these formal power series are defined in this way, so the coefficients an are going I'm going to suppose that they grow factorially, and these are not functions, as I repeated before. So you have to think about this as collections of numbers of these coefficients an. When the coefficients grow like n factorial, these are sometimes called Gevrey-1 series. So Gevrey-1 is because they grow like n factorial. There are Gevrey-2 series which grow like n factorial to the square, Gevrey-3 series n factorial to the cube. But most of the series that you find in quantum theory grow actually like n factorial, so I'm going to focus here on Gevrey-1 series. So now the first question you can ask is how you make sense of this object. As I said, this doesn't belong to anything that you know in kind of elementary mathematics, and you want to make sense of them. And then what people found is that you can do something kind of deceptively very simple but very interesting. So what I'm going to do is what is called Aborted Transform. So Aborted Transform is an operation, it's a transformation of this formal power series in which I do something very brutal. I just take these coefficients an, which grow factorially, and I define a new series in which I divide these coefficients by n factorial. So the factorial growth that I have at the very beginning is completely cut off, and typically this new series, which actually I'm going to write it in a different variable because it really lives in a different world, this series is going to have typically a non-zero radius of convergence around the origin. So this is actually very funny because it's a very simple thing, but we have passed from a world that we don't really know very much about, which is the world of factorially divergent series, to a world which we know, which are the world of functions which are analytic at the origin. And when a function is analytic at the origin, you have a very good starting point, and in particular, you can apply everything you know about complex analysis. Okay? So this is the first step. We will find, when given this formal power series, which doesn't make sense as a function, we will get this Aborted Transform, which is at least a function which is analytic at the origin. It's complex analytic at the origin. Okay. Now, once you have a function which is analytic at the origin, typically, you can try to extend this analytically to the full complex plane, and when you do that, you will for sure find singularities. You will find poles, branch cuts, and so on. So the picture you should have about this Aborted Transform is a function which is analytic at the origin, but will have lots of singularities in the Aborted plane, which can be of all kinds. Now, I will denote the location of the singularities. Remember that zeta is the variable that appears here. So this is the argument of this Aborted Transform. I will denote the singularities in the Aborted plane by this letter zeta with a subindex omega. So omega will actually label the different singularities. I will give examples in a moment. So just follow me for an instant, and then I will give you some concrete examples of this. Okay. Now, if we want to do something useful with these Aborted transforms, we want these functions not to be very wide. Okay. The technical requirement for these functions not to be very wide is what is called the Resurgent function property. Now, the Resurgent function property, which you can think about a property of the original Gevrey-1 series, is the following. Now, technically, the definition of this Resurgent function is the following. When you take a line going from the origin to another point in the complex plane, in any line you draw, there can be only a finite number of singularities, and you can always deform, you can always take a contour in which you can actually analytically continue these Aborted transforms by avoiding this singularity. Okay? So you cannot have too many singularities, you cannot have a dense accumulation of singularities, you have to be able always to avoid the singularities by a proper choice of your path. And actually this turns out to be a very simple property and quite generic. So let me give you a very simple example of this situation. What is the simplest formal power series which is factorially divergent? Well, it's just a series in which you have the coefficients being k factorial. So this is clearly a Gevrey-1 series. By construction, is the simplest Gevrey-1 series. And what happens when you do the Aborted transform? Well, when you do the Aborted transform, you just remove this k factorial, and you get a series which is just the harmonic series set to the k. Now, this series is clearly convergent at the origin, has a radius of convergence equal to 1, and you can analytically continue this function, essentially to 1 over 1 minus zeta, so you will find a single singularity, which is a pole when zeta is equal to 1. Okay? So this is the typical situation you will find. You have a formal power series, which is factorially divergent. You do this Borel transform, and you find a function which will have a finite number of singularities in the complex plane. As I said, this is very important because we are going from the world of divergent power series to the world of complex analytic functions. And this is extremely useful because you can use all your knowledge of complex analysis, even of the theory of Riemann surface, to actually try to deal with these Borel transforms. Now, why we do that? Now, one of the key ideas in this field is that the singularities of this Borel transform have information about your physical problem that was not manifest in your original perturbative series. So in a sense, you can think about the Borel plane as a rabbit hole in Alice in Wonderland, and going through this rabbit hole, you will find things that were not at all manifest in the original problem you started with. And let me give you a physical situation in which this happens and in which these Borel singularities turn out to give you information that was not manifest from perturbation theory. After all, we know that perturbation theory has many limitations. And actually, this idea of looking at the singularities of this Borel transform is a way of going beyond the limitations of perturbation theory, but starting with perturbative information. So let me take one of the most known examples of perturbation theory in quantum mechanics, which is the double Weld potential. So the double Weld potential, you can write it in this way. So I wrote it in this way because in this way you can see that when G is equal to 0, you get a harmonic oscillator problem. And when G is different from 0, you get this potential which has two minima, which are degenerate. They have the same value of the potential energy. And this is a problem that appears often in quantum mechanics and in quantum field theory. I'm going to consider it here in the framework of quantum mechanics. And then you can actually ask yourself, again, what is the ground state energy for this type of Hamiltonian? So you take the Hamiltonian P squared over 2 plus this potential, and you try to say what is the energy of the ground state. Okay? This is not an exactly solvable problem, but then you can use, again, perturbation theory in this variable G. Now, when you do this, you realize that your potential has two minima. So essentially, when you do perturbation theory, you have to expand around one of the minima of the potential. So here you have two minima, and then you can do perturbation theory around these two different minima. You get exactly the same perturbative series. And this is something that you can also calculate with elementary means. You will get, again, your series, a series which starts with 1/2, which is the energy for the harmonic oscillator, and then you will have an infinite series of coefficients, and you can see here that they already grow quite fast, and you can also see that this is a Gevrey-1 series. So this is a series in which the coefficients grow factorial. So you see that this is really very generic. This is a different physical problem from the one I started with, and again, we have a Gevrey-1 series. Actually, I think there is something missing here. There is some text missing here. Well, anyway, I think there is a test missing from my original transparency. So what happens now with this series is the following. If you do a Borel transform of this series and you look at the singularities in the Borel plane, you will find actually that these singularities tell you about some physics of the problem that is completely invisible in this approach. And the physics that you would find if you do the Borel transform of this series is actually the physics of quantum tunneling. You see here, you have classically what you have are two minima of this potential, and you can think that if you consider a quantum particle sitting near one of these minima, it will oscillate, and you will have some sort of perturbed harmonic oscillator sitting at one of these two minima. And this is actually what this perturbative series is trying to tell you. This perturbative series is trying to tell you that you have harmonic oscillator, but then you will have some corrections as a power series in G. But actually, if you look at the singularities of the Borel transform of this series, it's slightly more complicated exercise, and I won't do it here. But if you do that, you will actually learn something different. You will learn about quantum tunneling between these two minima. So quantum tunneling is this very highly quantum phenomenon in which a particle can actually go through a region which is classically forbidden and go from one allowed classical region to another. And this is something that you won't see in perturbation theory, but you can, at least directly, but you can see if you do this Borel transform analysis. So that's one of the reasons we are doing all this, because we want to extract information from the perturbative series which is not manifest in the original form of the perturbative series, but is going to be manifest once we go to this Borel transform. And in a sense, this is a way, in physical parlance, you say that this gives you access to the non-perturbative sector of the theory, to sectors which are not directly encoded in the perturbative series. And this will be a recurrent theme in these lectures, and I hope that will be clarified as will be even more clear as we go, as we progress in these lectures. Okay. So, so how do we extract this information about the Borel transform? Now, as I told you, when you do this Borel transform, you will find singularities in the complex plane. So what you have to do is to look at the local expansion of this Borel transform around these new singularities. In a sense, you see, if you think about this, original picture, the expansion of the Borel transform at the origin gives you the same information that you started with, which is the perturbative series that you started with. When you do the local expansion around these new singularities, you can hope to get new information which is not manifest in the original perturbative series. And this is what you have to do mathematically, and this is one of the kind of basic steps in the theory of resurgence. You have to do expansions around different singularities, and when you do this, you will get actually new formal power series. So let me explain you a little bit better how you do this. I'm going to focus, for simplicity, in what are called simple resurgent functions. So a simple resurgent function is a function in which all singularities are logarithmic branch cuts. Okay? So when you have a singularity, you could have a pole, you could have a branch cut, and you could have a logarithmic branch cut. So simple resurgent functions are the simplest cases, the simplest family of Borel transforms in which all singularities are logarithmic branch cuts. Now, if you have a logarithmic branch cut around the singularities, this means that if you expand this Borel transform about the singularity, you will get, this singularity is located at zeta equal to zeta omega. When you do this expansion, you will get a logarithm, and this logarithm will be multiplying a formal power series which will have a finite radius of convergence. And then you can introduce a multiplier here, a constant here, which I'm going to call S omega, and this constant will play an important role later on. But the most important aspect of this formula is that when you expand a logarithmic branch cut, you will get definitely a logarithm times a formal power series with a finite radius of convergence. So this I call phi hat sub omega. And then when you get, of course, you will get regular terms, but we're interested in what happens near the singularity. Now, after you do this, you see there are things missing here. Now, so this function here is analytic at the origin, but you can think about this as the Borel transform of a new power series associated to the singularity. So in a sense, you undo this, you start with a formal power series, which is convergent, has a finite radius convergence, but you actually think about this as a Borel transform, and then this will give you another power series with new coefficients A and omega, which will grow again factorially. And this is actually how the formalism works. You take your Borel transform, you expand it around the singularity, you will get, in this case of logarithmic branch cuts, you will get logarithmic branch cuts times a formal power series with a finite radius of convergence, and this power series, you think about it as another Borel transform, and then you get another divergent formal power series. So this is actually a very systematic procedure, and this is, this idea of rabbit hole. You start with a formal power series, a perturbative power series, you go through the rabbit hole, and you start finding more power series, which are actually different from the ones that you started with. So this means that this theory is already telling you something very non-trivial. It's telling you that when you actually work with a formal power series, this power series is not isolated, but it's just part of a structure of additional formal power series that are associated to singularities of these complex analytic functions. Okay? So this is kind of the formal power, this is the formal structure that you find in this way. And this is actually very interesting for physicists because we know that perturbation theory is not the last word on problems, and one way of actually getting more information is to do this procedure. Now, once you find new power series, which are divergent, you can just repeat. You go deeper in the rabbit hole, and you get more and more formal power series. And at some point, you find all power series in the game. And I actually will give examples of this in these lectures. At some point, you stop. There are no more new formal power series that you can get in this way. And what you get at the end is just a collection of formal power series that were, if you want, generated by your original one. Okay? So given a formal power series phi of z, you will find a family of formal power series that I label here by omega, with omega, small omega, it's labeled by some set capital omega. And this structure of formal power series is what I call a minimal resurgent structure. So that's already, if you want, the first surprise that you find in this game. That given a formal power series, you will start getting more and more formal power series that are associated to it. And these formal power series are not the ones that you calculated originally. And the question of what is the meaning of this formal power series is something that we will actually pose and try to answer later on. Now, if you have all these formal power series, remember that by assumption, I'm assuming that all these formal power series have just logarithmic branch cuts. So this means that when you expand these formal power series around their singularities, you will have a log multiplying another formal power series in this set. And then this constant I introduced before is going to be very important. This constant now form a matrix because I have, if you want, relationship between these formal power series in terms of a matrix, and this matrix is called the matrix of Stokes constants. It's going to be a very important ingredient in the game. But notice that the value of these Stokes constants depends on my normalization of the formal power series. But once you have chosen your list of formal power series, these Stokes constants are numbers, complex numbers in general, which are going to be completely determined. And these complex numbers are actually very important because they tell you how to go from one formal power series to the other. It's the matrix that relates all this structure of formal power series in the game. Okay? So you want the take-home message here is that also in quantum theory or in the study of ordinary differential equations, we just calculate at the very beginning one single formal power series. This formal power series is actually the first ingredient in a sort of cathedral of many different formal power series which are related by this Stokes constant. Okay? So this was very abstract, but let me give you a very simple example where this can be made completely explicit. So the starting point in the game is a formal power series, and I'm going to write a formal power series which unfortunately looks a little bit complicated, but if you are experts on special functions, you will recognize this series as the formal power series that you obtain when you try to calculate the asymptotics of the AD function. The AD function is a very important function, and when you try to calculate these asymptotics, you actually get this formal power series. You see here you have gamma functions, which grow like n factorial. So you have here n factorial times n factorial divided by n factorial. So this series, the coefficients of this series actually grow like n factorial, and this is actually an example of a Gebre-1 series, a relatively simple example. Now, one of the beautiful themes of this example is that also the coefficients look a little bit complicated. They have the property that the Borel transform can be computed analytically. And when this is actually a very simple exercise. You don't even have to think. Mathematica will do it for you. You just plug the Borel transform of this function in Mathematica, and you will get actually a hypergeometric function. So the Borel transform of this function is a hypergeometric function, which argument minus 3z over 4. So this is a function which is analytic at the origin, but has a singularity. We know that hypergeometric functions have a singularity, and if you plot the Borel plane structure of this Borel transform, you will have that they have a singularity exactly on the negative real axis at z equal to minus 4 over 3. Okay? So this is a very simple example of a Borel transform which can be analytically calculated. Usually, generically, we cannot do this. We cannot actually calculate the Borel transform analytically, but in this example, we can. Now, what is this theory of resurgence telling you? Well, the theory of resurgence tells you that hidden in this singularity, there is a new object, that it was not manifest in my original power series. And actually, you can see that the singularity here is a logarithmic singularity. So this function, this formal power series that I showed you, is actually an example of a simple resurgent function with a logarithmic branch cut. This is actually part of the standard theory of hypergeometric functions, that the singularity here will be of the logarithm type. Now, if you study the logarithm, the expansion of the Aborted Transform around this singularity, you will actually get a new series. And this new series is very, very similar to the original series that I found before, just has a different sign here. So my original series has a minus sign, so it was like an alternating series, while this series here doesn't have a minus sign. But it's a different series. So you see already that in this example, by looking at the singularity, you get a new object. And this is actually very interesting, because you see the 80 function actually it comes from the 80 differential equation, which has two independent solutions. And actually, this power series is, in a sense, the power series that will lead to the other solution of the 80 differential equation. So you see that already here, this game is giving you information which is global information of your problem, which was not manifest in the original power series that we started with. Okay? And it's actually very easy to calculate the Stokes constants here. With this normalization, you can see that they are just I. And this is an example in which everything is very clear. Okay? It's a quite neat example of this theory of resurgence. Now, it turns out that this example of the 80 function is just a particular example of a more general class of examples of Gebre-1 series, which are quite important in mathematics. And these are formal power series that appear when you study functions defined by an integral form. So the 80 differential equation can be actually solved by an integral formula, and you could have derived this formal power series by doing a saddle point approximation of this integral formula. So let me actually look at this type of functions that are defined by a one-dimensional integral of the form an integral of an exponential of some non-trivial function divided by a constant h bar. I call this h bar because it has, it will be related in some examples to the Planck constant when we put this in the context of quantum mechanics. But for the moment being, this is just a formal variable. And then, this define a formal function of this variable h bar. So, of course, here I'm not specifying contours for this integration. By depending on the function s of x, you can specify contours in the complex plane so that this gives you well-defined function and so on. But what I'm now interested on is not producing functions out of this, but producing Gebre-1 series. Gebre-1 series are just formal power series. So how could you actually obtain formal power series from this type of saddle point integral, for this type of integrals? Well, precisely using the saddle point approximation. Now, in the saddle point approximation, you have to look at critical points of this function, which satisfy s prime of x equal to 0, and then you do a Gaussian approximation around these saddle points, so you essentially expand this integrand around this critical point, and then you will find a formal power series that you can integrate term by term by doing Gaussian integration, and this actually is a very important source of Gebre-1 series. So when you do this saddle point analysis around these equations of motions, you will get typically Gebre-1 series. So if you consider, for example, a function s of x of this type with critical points which could be maxima or minima, as I said, doing this formal power series, you will get things of this type. So the leading term here, you will have an overall exponential, which is the exponential of this function x evaluated at this critical point divided by h bar, and this will multiply a formal power series. So if you have different critical points, the different critical points will give you different formal power series in this parameter h bar. Okay? So let's suppose that we just look at one critical point. So let's, for example, assume that we just look at the critical point x2, which in this example that I draw is a minimum. And you look at this formal power series, which is going to be generically a Gebre-1 series, and you try to do this game of looking at the Borel transform of this thing. Okay, what would you find? Well, actually, what you find is that the singularities, the first singularity that you will find in the Borel plane for this formal power series will be actually located at S of x2 minus S of x1. Okay, sorry, S of x1 minus S of x2. Okay? So what is very interesting here is that when you look at this formal power series here, and you look at this Borel transform tells you that there are other critical points in your saddle point integration that you didn't look at, but they are present there. So this is another example in which, by using this technique of Borel transforms, saddle points, the analysis around a local saddle point tells you about the other saddle points of your integral. And this is exactly this type of global information that you can obtain by doing this procedure. It's actually, you could actually rephrase this 80 example in this way. If you write the integral solutions for the 80 differential equation, you will find that this phi 1 is the formal power series associated to one of the critical points of this saddle point integral, while this phi 2 is the formal power series associated to the other critical point, and then this singularity of the first formal power series is telling you about the other critical point of this saddle point integral. So the idea then is that when you have different saddle points, even if you only want to look at one of them, this Borel transform of this formal power series will force you to take into account the other saddle points that appear in the theory. So essentially, this tells you that you can have a global picture of your problem by looking at these Borel transforms. And what is interesting about this, so this is a plot here that I just rephrased this thing that I'm saying. If you look at the Borel transform of phi 1, you will find the action of the second critical point, and vice versa. If you look at the Borel transform of phi 2, you will get the action, or sorry, the action, I call x the action here. X is the function. This is physical deformation. So x is the I call it the action function. So you will get the function x evaluated at the other critical point. So you see that Borel transforms know about the global landscape of critical points, even if you started just with one of them. And the reason why I'm telling you this is because in quantum mechanics and in quantum field theory, we actually do something which is very similar to this, in the sense that we usually write many answers to our problems in terms of path integrals. And path integrals can be regarded as infinite dimensional generalizations of these one-dimensional integrals. And actually, when you look at a path integral in quantum field theory and quantum mechanics, what you do very often, and this is what quantum field theory courses are essentially about, you essentially do a saddle point analysis of the path integral around one critical point, and this gives you a perturbative expansion. And what I'm telling you is that when you do this Borel transform analysis of this type of perturbative series, you will get information about other saddle points of this path integral that you actually were not aware of in many cases, or you actually didn't that were not essentially explicit in your analysis. Okay? So this type of formal analysis of saddle points, as I said, generalized to path integrals in quantum mechanics and quantum field theory, and this is going to be useful in later on when I look at quantum knot invariants. Okay, so far what I told you is that, yes? 5 minutes, okay. So far what I told you is what is the structure of these Borel transforms. So already this is quite surprising from many points of view, but I didn't solve the problem that I stated at the very beginning. At the very beginning, I told you that if you have a formal power series, you don't know how to make sense of them. So the Borel transform is not really a direct solution to this problem, but it's an interesting step in solving this problem. So how do you actually solve the problem of making sense of formal divergent series? Well, you have to do a next step, which is not the Borel transform, but it's called the Borel resummation of the original phi z series. So formally, you do the following. So the Borel resummation of phi z is defined essentially as the Laplace transform of the Borel transform of phi evaluated at the argument x times zeta, and you do a Laplace transform with respect to zeta. Now, here x can be a complex number, so if you actually consider the argument of x to be equal to theta, and you consider a line in the complex plane which goes along this angle theta, so this is a ray which starts from the origin and goes to infinity around with angle theta, you can actually write this Laplace transform as an integration around this ray of the Borel transform of my original power series times this exponential here, and when I factor 1 over x. This is just a trivial change of variables. Now, this is a definition, but of course, you know, this integral will not always exist. Now, in order for this integral to exist, you have to make sure that the analytic continuation of this Borel transform decreases sufficiently fast around this ray in the complex plane. Now, when this is the case, and when this analytic continuation doesn't have any singularity along the integration path, this Borel resummation exists. And what is very impressive about this Borel resummation is that this, when it exists, defines a function of x, and this function of x actually, let me just, this function of x actually has an asymptotic expansion around the origin which reproduces the original function phi of x. So essentially, remember that phi of x was a formal power series. Now this Borel resummation is a function, but the asymptotic expansion of this function, the asymptotic of this function at the origin is exactly the formal power series that you started with. So if this Borel resummation is well defined, it actually makes sense of your original formal power series in the sense that its asymptotic expansion reproduces your original formal power series. Okay? So this is, in a sense, one of the most traditional ways of making sense of this divergent formal power series through this Borel resummation. So actually, the Borel transform is actually the inverse of this Borel resummation, is actually the inverse of the Laplace transform. And in a sense, what you are doing here is reconstructing a function which has the asymptotics that you started with. Okay? So this means that, for example, if you are lucky and you calculate all the coefficients of this perturbative energy for the ground state energy of the quartic potential, if you are lucky and you calculate many of these coefficients and you calculate this Borel resummation, this will give you a number which is, if you are lucky again, the actual energy of this problem. Okay? So remember that when we started this lecture, I wrote for you this formal power series, okay? And this formal power series now could actually lead to an actual function of G if you do all these procedures of doing first a Borel transform and then a Borel resummation. And actually, in many examples, this actually works and gives you a function, not just a formal power series, which calculates what you want. But actually, if you think about this formal Borel resummation, you have to be very careful, because it might happen that even if this function decays sufficiently fast, remember that this function, this Borel transform, has singularities. This was actually the main point at the very beginning of my talk. So when this function has singularities, you have to be very careful. And this means that when the angle theta is such that this ray goes through a singularity of this Borel transform, this Borel resummation doesn't make sense anymore. Okay? So there is a price to pay, and this is always the case in life, that there is always a price to pay. So you can actually make sense of this formal power series and do a Borel resummation, but there are singularities of this Borel transform that will be obstructions to actually define this function. And maybe that's a good point to stop, and tomorrow I will continue the discussion of this, and we will see how to deal with this situation in which we have singularities which obstruct this operation. Okay, thank you very much.
So thanks to Marco's perfect timing, we have time for maybe a few short questions.
Thank you. A very basic question. Is there something special with the factorial? Would the theory work if we divided for a different function than the factorial?
Yeah, the factorial, that's a very good question. Now, the factorial is just the fact that, when you study quantum theories, typically you have polynomial perturbations of your original theory. For example, you think about this quartic potential that I started with. You see that this is a polynomial perturbation of your original Hamiltonian. When you have polynomial perturbations, typically the series that you obtain grow like factorial, and that's why you want a theory that takes care of factorials. But you could think about more general perturbations of your Hamiltonian, which would give you worst divergence of factorial. Now, for this worst divergence, you have to develop a more general theory than this one, in which you account for this higher divergence. But the fact that I'm focusing on factorials is because that is a generic fact of quantum theories that polynomial perturbations give you to factorial growth of perturbative series. I don't know if this answers your question.
Thanks a lot. Let's thank Marcos again, and then we'll take a 10 minutes break.